Hello, today's presentation is about Auger Electron Spectroscopy and Electron Microprobe Analysis. It is by Group 2 for Dr. Tasooji's MSE 420 Spring 2014 lecture. During the course of this presentation, we will discuss the design, mechanisms, limitations, resolutions, and capabilities, and finally, the applications of both techniques in sort of a compare and contrast fashion. So, let's get started.
Here we have the apparatus used to perform Auger electron spectroscopy. At the top of the image is the focusable electron gun. The electron gun shoots an electron beam at the sample, which interacts with whichever material we are wanting to characterize, and that material then emits electrons due to the Auger effect. The cylindrical mirror analyzer analyzes the emitted electrons, and the information may be used for characterization of the material. AES may also use a spherical electron analyzer, not as depicted in the image. This process takes place in an ultra-high vacuum environment in order to reduce adsorption of gases onto the surface of the sample, which would alter the readings. This is the Electron Microprobe Analyzer. Similar to AES, it uses an electron gun. However, this characterization tool creates a weak beam of electrons using a tungsten filament. The weak beam accelerates across a high voltage anode and is focused using magnetic lenses. When the beam interacts with the sample, X-rays are produced at a characteristic frequency to that material. The X-rays are then analyzed in the spectrometer and can be used to characterize the material. Different electron microprobe analyzers use either wavelength dispersion spectrometry, WDS, which tunes into specific X-rays, or energy dispersive spectrometry, EDS, which counts all the emitted X-rays at once.
My name is Laís and I will talk about mechanisms of EMPA and AES characterization tools. For both techniques, it uses electron beam where a tungsten or lanthanum X-bright filament emits electrons. The result is a beam which has to be focused on the sample. After that, there are different areas in the sample. They are split as you can see on the figure. Each of these areas emit a different sign from a sample. The main different types of interaction are shown in this picture. These different sample interactions emit different signals. Each technique uses a signal for character one of these areas. So, what are the similarities and differences between EMPA and AES? Both techniques are determination of the composition of the sample. Both use an electron beam. AES is a technique is more superficial, with its own angstroms, whereas EMPA is deeper and can reach components until 100 nanometers. This figure is showing EMPA schematic. The sign identified by this technique is X-ray, up to 3 microns, and depth of the sample. The signal can be captured by two different spectrometers, EDX or WDX. The difference between them is that WDX move depends on the angle between the sample and beam. They are made by silicon and lithium crystals. The next figure is showing an example of EMPA ADX diagram. This image is showing the AES schematic. To determine the composition of the surface sample, you have to use an argon million gun. The detector captures the signal and transmits to the monitor. The CMA cylindrical mirror analyzer can be replaced by HSM hemispheric analyzer. And the last figure is showing an AES spectrum. As we can see, the component peaks are so close that it makes it difficult to identify each one separately.
The chemical resolution for EMPA is 100 parts per million. The lateral or spatial resolution is 1 micron, and the penetration depth is also 1 micron. The capabilities for EMPA are that it provides qualitative and quantitative elemental analysis of solid samples, and it can be used for any solid material. So conductive samples just need to be well polished and flat, and non-conductive just need to be coated with a thin layer of carbon. So the sample preparation is relatively quick and easy, and the average sample size is 25 millimeter diameter and 10 millimeter thick disc. It's a non-destructive method, and elemental compositional mapping of areas are on the order of millimeters. So the quantitative elemental analysis for sodium and heavier elements is highly accurate, and the analytical result turnaround time is fast. So the combination of the chemical and spatial resolution allows for a highly accurate, spatially specific, and rapid analysis of heterogeneous samples. Some of the limitations for EMPA are that the sensitivity or the chemical resolution is considered only moderate. It's exceeded by techniques like SIMS. And there's only qualitative analysis for elements boron through neon 5 through 10, no quantitative analysis. And the lateral resolution and the penetration depth are limited by the electron scattering that's in the sample, so there's really no way to improve on those resolution limits. Because the specimens need to be flat and polished or the carbon-coated samples, analysis of fracture surfaces, films on substrates, and individual particles is possible, but it does have a greater uncertainty.
AES in general is used for chemical composition analysis. Typical resolution values would be 10 to 30 nanometers for lateral, which is pretty high, but the depth resolution is only 0.5 to 5 nanometers, which is one of the reasons why AES is used primarily for surface analysis. The sensitivity for most elements in AES is 0.1 to 1 atom percent, but this can vary by machine. The capabilities of AES, as mentioned previously, are surface analysis, so things like determining phase compositions, grain boundary types of analyses. This is generally done on smooth samples, and depth profiling can be done as well. This can be done on rough or smooth samples. And what I mean by depth profiling is you basically list the composition as you go down into the sample from the surface. It can be used for thin films, and in general is just a pretty solid surface analysis technique. One of the good things about it is that it can detect low atomic number elements except for hydrogen and helium, which is better than EMPA. Other limitations, besides not being able to detect hydrogen and helium, include possible electron beam damage to organic and some ceramic materials, so be careful with your biological and polymeric type samples. The electron beam itself also limits analysis for highly insulating materials because of the surface charge that occurs. Also, sometimes, especially for low Z elements, there are electron beam artifacts in your collected data. So all in all, AES is a pretty solid technique with some advantages and disadvantages when compared to EMPA.
Auger Electron Spectrometry. It's used for surface-sensitive analytical techniques for dealing with surface chemistry. This provides information on composition of the outermost atomic layer and is used primarily to investigate interactions between solid surfaces, metals, organic materials, and biomaterials. This is of particular interest for one application of corrosion resistance. One example in the automobile industry is the use of AES corrosion analysis specifically for cold-rolled steel. When AES is used, it found high concentrations of carbon, iron, and oxygen, which can lead to corrosion and rust. So with the help of AES, they are able to determine new and better ways for the body of the car and other components of the car to last much longer. Another application for AES is thin passive films. Thin passive films have little to no reaction with their surrounding environment. The passivity forms as a result of the slowing of the reaction rate. A thin passive film is a good candidate for AES since we're only dealing with the outermost atomic layer. Since only analyzing a thin surface, we can get good results for chemical makeup. EMPA, used in analysis of elements 11 and up, used for compositional analysis of individual phases in multi-phase samples. One study of ceramic nuclear waste. The use of ceramics in nuclear waste has been useful for both handling and storage of nuclear waste.
is essential to the study of the microstructure for characterization to know how to proceed with the waste. One drawback to this is the prep time. It is very long and it's very difficult, and it can be, so it's very harmful and high risk for the user. The last application I'll be talking about for EMPA is failure of aluminum wire connections. This was specifically interesting because it was due to overheating of the circuit, and this affected primarily residential areas. The use of EMPA allowed for the metallographic sectioning, and this was done by chemical analysis, which can be seen using EMPA. This allowed for the problem areas to be identified and fixed.